Hey everyone, so let's get on with the topic at hand, which is work, and now we're going to extend what we've done to non-constant forces. So let's quickly review what we did before. We started out talking about work done by a constant force. So here's a woman pulling up on a crate with a force F, and the box is displaced, has a displacement D. So if you have a force F and a displacement D, then you have work being done. Work is equal to F dot D, right, where the dot is the dot product, otherwise known as the scalar product. And it is equal to, right, the magnitude of the force vector times the magnitude of the displacement vector times the cosine of the angle between the two. So here's the angle there. Work is a scalar quantity, and it has units of joules. A joule is a Newton times a meter, or in MKS, that would be a meter, meter squared or second squared times a kilogram. We also talked about scalar products. Actually, that was last week, or dot products. So A dot B, right, for any two vectors A and B is equal to the magnitude of A times the magnitude of B times the cosine of the angle between the two, right? And it can also be written out in terms of AX BX plus AY BY, right? And it was this way to multiply two vectors together to get a scalar that depends on how large the vectors are, how long they are, and how much the extent to which they point along one another, right? So two perpendicular vectors have a dot product of 0. Two vectors that are parallel with each other, pointing in the same direction, have a maximal dot product, and two vectors, say, pointing in the opposite direction from one another that are anti-parallel like this, will have a dot product that is negative, right? And it's the maximally negative in that case. Finally, we talked about kinetic energy and the work energy principle, or the WEP. So the WEP says that the net work on an object is equal to the change in the kinetic energy of that object. And kinetic energy is the energy due to motion. It is 1/2 mv squared. So 1/2 mass times velocity squared. So you can see if the net work done on an object is positive, then you will have an increase in kinetic energy. And if the net work is negative, then you'll have a decrease in the kinetic energy. So energy is basically the ability to do work. So mechanical energy is the ability to do work. So you've heard of energy before. This is the precise definition of at least mechanical energy. So work and energy, they both have the same units, right? They're in units of joules. Now let's talk about something important that I kind of forgot to mention last time, which is the work done on an object, say, versus the work done by an object. So here, right, you see a moving hammer that hits a nail. Let's say that the hammer hits the nail, drives it in, and then the nail comes to rest. So the hammer exerts a force F on the nail, right? But then that means that the nail is going to exert a force on the hammer that's equal and opposite to it, right? That's Newton's third law. So the work done on the nail by the hammer here is going to be positive, and the net work done on the hammer by the nail will be negative. So right, the displacement of both of them was in the same direction. They were both displaced in this direction while they were striking one another, right? F dot D, so since the force was this way on the nail, F dot D, then F and D are along one another. So this is going to be the force times the displacement, and it's going to be a positive number. But the force that was acting on the hammer, right, was going in the opposite direction. It goes this way. So F dot D for the hammer, for the nail here, for the hammer, right, since the force is going to the left for the hammer and the displacement is still going to the right, this is going to be a negative number, right, for the hammer. So we could talk about, say, the work done on the nail, say, by the hammer, and that would be this. Or we could talk about the work done on the hammer by the nail, right? And that would be this one. It's important to keep this distinction, right? The work done on something by something else. That's important. So let's just say that I have a piston in an engine, and it goes down, say, and it compresses. So there's a force. There's a force exerted, say, up here by some, there's a spark plug here, and it explodes, makes a little explosion, and that forces down the piston. Then when you look at the gas down here, right, there's this force that displaces it in this direction. The work done on the gas in this case, is going to be positive, right? This is a positive number. But you can also talk about, say, the work done by the gas on its surroundings. So the work done by the gas on its surroundings is, well, the force that the gas down here, say, does on its environment would be equal and opposite, right? So it's going to resist this motion of this piston. So you're going to get a force going up, right, to resist this motion. But yet, right, the displacement vector, which I'll put in green, is still going to be down in this direction, right? That's the displacement. So then if this is that's the force there. So the work done by the gas is going to be equal to F dot D. Well, F now and D are going in opposite directions. So it's actually negative magnitude of F times the magnitude of the displacement D. So this actually shows, right, that the work done by the gas is equal to minus the work done on the gas. So this distinction is especially important in the case of thermodynamics, where you start talking about these kinds of things a lot. But it's important to make this distinction, the work done by something and the work done on something. Usually in Physics 1, we stick to asking you questions like, what is the work done on this object? But the work done on an object is always minus the work done by an object. All right, so here is how you're going to solve problems using work, right? You're going to do a free body diagram like you always do. You're going to choose a nice coordinate system, and then you're going to apply Newton's laws to determine any of the unknown forces. And then you can find the work done by each of the specific forces, okay? And then you can find the network, which could come in one of two ways. So if you have two forces, say F1 and F2, then you could talk about the work done by F1, and you could add it to the work done by F2. Okay, that would be that's equal to the network. You could also talk about the net force, right, which is equal to F1 plus F2, and you could say, well, the network is just F net dot this dot with the displacement, and you could do it this way. So these are equal to one another, right? You could take the net force and find the work done by the net force, or you could take the work done by each of the individual forces and sum those together to get the net force. So the sum could come in at the level of the force, or the sum could come in at the level of work. Either way, you get the same answer in the end. And then you can apply the work energy principle if you're asked to, say, find change in kinetic energy, or say find some final speed from some initial speed. Let's do some real quick conceptual problems before we go on to talking about non-constant forces. So for all of these, I'm just going to introduce the question, and then I want you to pause the video, think about it yourself, and then see what my answer is. All right, so here we go. Problem 1. Is it possible to do work on an object that remains at rest? Pause, think about it yourself. So the answer is no. right? So work requires that a force acts over a distance, right? If work is force dot displacement, well, if displacement is 0, which is what it means for something to remain at rest, then F dot D is going to be 0 as well. Next up, a box is being pulled across a rough floor at a constant speed. What can you say about the work done by friction? Pause it, answer it for yourself. So in this case, right, friction does negative work because friction, right, is going to resist motion. If you have motion along a surface, right, friction is always going to resist that motion, right? Friction is always going to resist it. So friction is going to do negative work when the displacement, say, is going this way, and friction is going to resist that motion of the object sliding across the surface. Now, can friction ever do positive work? This is a good question. Pause it, think about it for a second. Yes, the answer is yes, right? So here it gives you an example. Consider the case of a box on the back of a pickup truck. If the box moves along with the truck, and it's not pressing up, say, against the sides of the pickup truck, but it's just the friction between the truck and the box that is carrying it along, then yes, the force of friction is doing positive work on the thing. So if something is sliding across the surface, then friction is always going to be doing negative work. But that doesn't mean that static friction, say, or even kinetic friction, can't cause something to move along in the direction of the displacement, but it's just that the surface itself would have to be moving. All right, so in a baseball game, the catcher stops a 90-mile-per-hour pitch. What can you say about the work done by the catcher on the ball? So is it positive work? Is he going to do negative work? Or is he going to do 0 work? Pause it, think about it. So the catcher is going to do negative work on the ball, right? So as the ball comes in, right, here's the glove. As the ball comes in, right, it's going to hit this thing. It's going to displace it this way, right? But it's going to go, right, the force exerted by the glove on the ball is in this direction here. So F and D are anti-parallel. So you're going to get negative work done on the object. Now, another way that you can actually think of this is in terms of the work energy principle, right? What is the net work, say, when the initial speed, the ball had is positive, and the final speed of the ball is equal to 0. Well, the 1/2 mv final squared minus 1/2 mv initial squared is going to be, well, if v final is 0, then this term is equal to 0. And if v initial here is non-zero, then you're going to get a negative number here. So there's two different ways of thinking about it. Both of them, of course, lead to the same conclusion. Now, a ball tied to a string is being whirled around in a circle. I think I did this in a lecture a couple times, right? So it's being whirled around in a circle. What can you say about the work done by the tension in that string? Pause it, think about it. So the tension does no work at all, of course, because as we talked about something very similar to this last time, right? The tension force is pushing in towards the center the whole time. The displacement is always perpendicular to that, right? It's always going along the circular path. So the displacement and the force are always going to be perpendicular to one another. So the amount of work is always going to be 0. Okay, I think this is our last one. A box is being pulled up a rough incline by a rope connected to a pulley. How many forces are doing work on the box? Okay, pause it. Draw a quick free body diagram, just roughly, and see what you think the answer is. So the answer here is 3 forces, right? There's a force of friction that's resisting motion. There is a normal force in this direction. There is a weight, say going this direction. Let's just use mg. And there's, of course, tension pulling up here. Well, if the displacement, let's use green for the displacement vector. If the displacement is in this direction, say, then friction is going to do negative work, and weight is also going to do negative work. Tension is going to be the one that does positive work, and normal force is if the object is sliding along the surface, then the normal force, which is normal to the surface, normal is another word for perpendicular, then the work done by the normal force for an object sliding along a surface is going to be 0. Okay, and the slides agree with me. All right. You lift a book with your hand in such a way that it moves up at a constant speed. While it is moving, what is the total work done on the book? Think about it. And the answer, of course, is 0. Why? Because the velocity is constant, right? You're going to have net work being 0 because, although the work done by your hand is positive, the work done by gravity is negative, and the sum of the two is going to be 0, right? F hand here has to be equal to mg in order for you to actually raise this thing up at constant velocity. So, right, the kinetic energy of the book does not change either, so that just gives you a tip that the velocity, since the velocity is constant, that the work done has to be 0. All right, finally we can get on to the main event for today, which is the work done by a varying force. So, a particle acted on by a varying force has a little bit of a complication to it. So let's let's show this path here. This will be our displacement. Okay. Now, if we have a force that is, say, acting on this thing as it moves along, if the displacement is not constant, or if the force is not constant, then we can't just take and do this, F dot D thing and say, well, this is a constant value and it would be the same everywhere. But what we can do is, say, take a whole bunch of little pieces along the displacement vector, and we could maybe divide up this displacement into little tiny elements here, as is shown. And maybe we could take the dot product between, say, the force that's acting right here, F1, and this little displacement element right here. I need a new color. So this little displacement element here. And then maybe we could take the force, say, here at F2 and take the dot product between that and this little displacement vector here, D2. And so this would, say, be at an angle θ2. So we could maybe get our work this way by dividing it up into a whole bunch of little pieces and taking, say, F1 delta L1 cosine θ1 plus F2 delta L2 cosine θ2 plus etc. But you who are familiar with calculus might be getting deja vu here as I'm writing this, because this probably looks like something that you might have seen before. For those of you who are new to calculus, you might at the very least have heard math professors tell you about chopping things up into little pieces and then summing them together. That is a very calculus-like way of speaking. So let's say for a force that varies, the work can be approximated by dividing the distance up into small pieces and then finding the work done by each and adding them up. So let's just I gave you the first two terms of this thing here. But let's just think about what this would look like if you had, say, a force versus distance plot, right? Where you took just the component of the force that's along the distance or the displacement element at each point, right? You would get something like this. And when you take the sum then underneath each one of these things, well, if the height of each one here is going to be, f at that specific point, say times cosine at that specific point, and if the displacement element, say, is this tiny little, the width of this tiny little rectangle here, then when you take and multiply those two things together, what you have is like the area of a rectangle here. And when you sum this all up, right, across all, say, 7 elements, what you get is this area underneath each one of these little rectangles here. And if you were to take, say, instead of 7 different rectangles, but instead chop these things up so that they're infinitesimally small, so you go from this finite width to, say, an infinitesimally small displacement element dl, then what you would get is an infinite number of infinitesimally small rectangles, and you would just get exactly the area underneath this curve. So the area under the f cosine theta versus distance curve would give you the work done by this varying force. So, of course, there is a word for this, as you're familiar with this already from me having covered it in the kinematics, in the context of kinematics. That word for the area under a curve is an integral. So in the limit, right, that these pieces are infinitesimally narrow, the work done is the area underneath this curve, right, which is the integral. So I can take an integral now. Notice I'm integrating over a displacement element from my initial starting point, A, to my final point, B. And so this is what I'm integrating over. My integrand, the function that I am integrating over, is this f cosine theta. So f cosine theta here, by the way, could be written as, if you wanted to keep this in its vector format, this whole thing here, if you wanted to save from having to put an angle in there, because you might not know the angle, could just be f dot dl, where this differential displacement element now is a vector element, right? So it's infinitesimally small, and it has a direction on it now as well. So this here, these two things are exactly the same. F cosine theta dl is exactly the same as f dot dl. So writing this in the most kind of compact form, it looks like this. Work is an integral of f dot dl from A, its starting location, to B, its final displacement. So this is the formula, the official formula for work, say, that will work all of the time, okay? In the limit where the say force and displacement are constant in time, are not varying, say, as the object moves, then this will reduce to, well, if f is constant, you can pull it outside of that integral, and you would just have f dot, and then you would have this integral, say, from A to B over this dl. So that you can do that so long as f is not changing with displacement. You're allowed to do that by the rules of integrals. And if the displacement, say, here is a constant value, then this is just going to be the overall displacement. So then you would have an f dot with a d, where d here is just the total displacement vector. And in the super simple case, say, where f and d are parallel to one another, you can write the thing that you probably learned in high school, which is that work is force times distance, which is only true in the most simple case. this formula here, always true. So if you want to remember, have to remember less formulas, just remember this one. That's all you need to know. Okay, so this might look a little intimidating to you because there is an integral and a dot product in it. And this is why I wanted to cover integrals last week and I wanted to cover dot products last week, so that this week, when I put this formula up here, everybody wouldn't be freaking out and just be overwhelmed by the amount of mathematics they have to learn just in order to comprehend the formula, let alone be able to apply it to a problem. So hopefully by now you've understood how integrals work, and at the basic level, right, for the most part, we're going to be using polynomials. So, say the integral of some ax to the n plus b x to the m dx is going to be a x to the n plus 1 over n plus 1 plus b x to the m plus 1 over m plus 1. For the most part, this is like the only integral that you have to remember, right? It's for the integral over a polynomial. Okay, so let's also just talk about this in one more thing, one last thing. So dl, if you don't like writing out this displacement element dl in this way, you could just note, right, that this displacement element is like a displacement element that has just 3 different components, a dl. There's a displacement element in x, one in y, and one in z. Sorry, I forgot the little d's here. I can just draw them in. And you can take then, let's say that you have your force F, you could write it out in terms of its 3 components. You can take your displacement element, write it out in terms of its 3 components. And you can take your positions, right, A and B, and write them out in terms of their 3 coordinates. So say you're starting out at point A, which has coordinates ax, ay, az. Then you could write it out this way. Work is the integral from ax to bx of that x components, plus ay to by for the y components, plus az to bz for the z components here. So this, if you remember the formula for the dot products, where you take the product of the x components plus the product of the y components plus the product of the z components, then this probably won't be that surprising to you that you can expand this version out this way. Okay, so this probably looks pretty abstract right now, but let's get concrete and apply this to specific problems. All right, and here's a very important problem. The work done by a spring force. So there's going to be more springs showing up in our problems from here on out. And the reason why is that we didn't use springs very much before, because springs are a non-constant force, and that makes them more complicated in terms of the mathematics that you need to do in order to understand them. So now we have this in our toolkit where we can work with non-constant forces more easily. So let's talk about the work done by a spring. So here I have an unstretched spring. Remember, if you displace it a distance x from x equals 0, where it's at equilibrium, say at x equals 0, then you're exerting this force Fp out this way. The spring is pulling on you with this spring force in towards the center, right? And I always like to write it this way. Spring force is minus k times the displacement from the equilibrium position. Okay. And so, right, if you're pulling it out, it pulls in on you this way. If you're pushing it in, it pushes. If you're pushing it in this way, then it wants to go back to its equilibrium point. So it'll push back on your hand in the other direction. Okay. Now, the force exerted by the spring is given by this. So let's talk about this calculation. So clearly the spring force is not constant with position, right? It varies with position. So it's minus k times this x component here. We set the equilibrium point to be where x is 0. So we have, right, you could write it this way as minus k times the coordinate x times I hat. So I hat the unit vector along x. Then we have, of course, the force of the person is going to be minus the force of the spring constant, right? Fp is the work, or is the force that's going, that's opposing the spring force, right? If you pull it this way, it pulls you that way. So this anyway would be negative the spring force, or it's positive kx in the I hat direction. So if we make a plot of this then, right, so this is Fp here on the y-axis and x on the x-axis, you'll see this is not a constant force, right? As the displacement, as the spring is displaced, the force increases and increases and increases. So we can't just use a simple Fp dot, dot displacement, right? I mean, which Fp would you use? This one or this one or that one? Like, you wouldn't be able to do that. So instead, you need to go to this other form where you're saying, I'm going to take an integral from the initial point to the final point over Fp dot with a displacement element. Okay. Now the displacement element is going to be, since there's only displacement in one direction, you can write dl as just, it's just x, or it's just dx I hat, right? The dy, the dz are going to be 0 because there's no displacement in those directions. So we have just dx I hat. So what then would be our dot product? So if we have Fp, which is a function of x, and it's entirely an I hat, right, over here, and we do dot dx I hat, well, it's just going to be Fp of x dx, right? Because the I dot I part, these are unit vectors. They're the same unit vector. So it's just 1. And our initial location was at x equals 0. And our final location, we're just going to shorten that to x. So this is the work done by the force of the person who's pushing or pulling on the spring, dx. So integral then over Fp dx, well, Fp was k times x. So we can put that in there. And then our integral is, k is constant, so k can go outside of the integral. Equals k integral 0 to x of x dx. And what's the integral of x? Well, it's, x squared over 2. And we can evaluate that, say from x, its final location to 0 at the bottom of the range. So that's going to be, right, 1/2 kx squared minus 1/2 k 0 squared, or in other words, that's 0. So we get 1/2 k x squared. That's the work done by the person pushing on the spring of spring constant k. Okay, now, since we've talked about this, let's do an example. A compressed spring example. A horizontal spring has spring constant of 360 newtons per meter. How much work is required to compress it from its uncompressed length, say it's x equals 0, that's the equilibrium point, to x equals 11 centimeters. And if a 1.85 kilogram block is placed against the spring and the spring is released, what will be the speed of the block when it separates from the spring at x equals 0? So here we're compressing the thing, right? We're going to compress the spring, and then you're going to let it go. The block gets released. The spring is going to like push against the block all the way up until it gets back to x equals 0. And then, say at x equals 0, the box will get flung out away from, say, sliding along this surface. It'll get flung out away from the spring. And we want to know, what's going to be the speed of the block? Well, we can use the work energy principle to figure that out. And it tells us to ignore friction. And then it says in part C to repeat part B, but assume that the block is moving on a table and that there's some kind of a constant drag force or, a friction force that's acting on it to slow it down. So why don't you pause the video and just think about this. I know it's the first time seeing this before, but remember, we already derived this, 1/2 k x squared. Okay, so pause, think about it for a bit, and then hit play. Okay, so let's do this calculation. So the horizontal spring has a spring constant of 360 newtons per meters. How much work is done or is required to compress it from its uncompressed length to 11 centimeters? So now we're just going to take, we're taking a hand and we're pushing it in this way. How much work is required to do this, to push it, say, 11 centimeters from its location? Well, we could just, go through and apply this integral from a to b of the force, right? But we already kind of did that, and we just came up with that the work done by the force of the person pushing it is 1/2 kx squared. So let's just plug our numbers into here. So 1/2 times, well, k is 360 newtons per meter. X I converted right from 11 centimeters to 0.11 meters squared. So how much work does it take? Well, it takes 2.178 Newton times meters, right? So a Newton per meter times a meter squared is going to be a Newton times a meter. There's another word for that. It's called joules. So there we go. Just plugged the quantities into that integral that we just did. So remember, this is the work done by Fp in compressing the thing. So don't look at this. This is the work done by Fp in compressing this thing. The work done by Fp on the spring. So this is not the work done by the spring. This is the work done on the spring. Okay, now on to part B. So if a 1.5 kilogram block is then placed up against the spring and the spring is released, what will be the speed of the block when it separates from the spring at x equals 0? So now, in part A, we were kind of loading the spring. We were doing work on the spring with our hand. Now in part B, it's the spring's turn to do positive work on something else. Okay, now the thing is loaded, right? So we did, so how much work was done, say, by the spring? Here, let's start out here, just looking at another way of talking about part A. How much work was done by the spring? In part A? Well, it was just minus the work done by the force of the person, right? Because the displacement is exactly the same. The displacement vector goes this way, right? But the force of the person is in this direction. That's Fp. Whereas the force of the spring is equal and opposite, right? It's in that direction. So the only thing that's different here between Fp and Fs is that they're pointing in different directions, or in other words, there's a minus sign on the force. So the work done by the spring is equal to minus the work done by the person. So in this case, you can see the work done by the spring here is this negative number, the work done by the spring. Now, when the spring is now we can look at this over here. So now, when the spring is allowed to exert its force and actually displace an object, then the displacement is going to be in the same direction as the spring force. So that's the case in part B. So here, the work done by the spring is going to be positive, right? The work done by the spring on the object is going to be positive. So, and it's actually going to be exactly the amount of work done by the person in part A. So W, say, of the force of the spring, say, when it's released, is going to be equal to the work done, say, by the person when it's compressed. Okay, so how do you know that? Well, when the person was pushing on this thing over here, right, they were compressing it, and the spring force was pushing back because that the amount of that force, say, was dependent on how far it was from the equilibrium position at any given point, right? Well, now the equilibrium position just is reversed. It goes in the opposite direction, So the magnitude of that spring force is going to be exactly the same at every point as the thing is being moved, say, from, as it's being moved towards now its equilibrium position. Let's say this is like x equals 0. So we have exactly the same magnitudes of the spring force during when it's released as we did as when it was compressed, but now the displacement vector is in just the opposite direction. So that's why the amount of work that the spring force does on the block when it is released is equal to the amount of work done by the person's hand when they compress the spring. Now, I can't help but get a little bit ahead of myself here. So in Chapter 8, we'll talk about potential energy and elastic potential energy, the potential energy that is contained, say, in a spring. You can kind of see how when this person is doing work on the spring, they're like compressing this spring and they're like almost putting something into the spring, right? That thing is called potential energy. And then when the spring is released, it does work on something else, right? It brings about this kinetic energy, right? Because it does work on something by the WEP. Work is equal to the change in kinetic energy, right? So it's actually when this work is being done, we could use the language of energy instead of the language of work to say, well, when the hand does work on this spring and compressing it, it stores up this elastic potential energy, and then once the thing is released, it then converts that potential energy into kinetic energy of the block when it's moving. So that would be another way of talking about this. The language of work and the language of mechanical energy are equally valid. Anyway, but that was just kind of getting ahead of myself. So the whole point of that was just that the work that is done by the spring force on the block is equal to the work that was done on the spring by a person's hand in part A. So that's going to be 2.178 joules. Now it's asking us to find the speed of the block when it separates, say, from the spring. Well, by the WEP, the net work done on an object is equal to 1/2 mv final squared minus 1/2 mv initial squared. Well, if the box is initially placed there at rest, then v initial is going to be equal to 0, right? So what is the final speed? Well, let's just multiply both sides of this by 2 over m. 2 over m w net is equal to the final squared. Okay, now I'll take the square root of both sides. Okay, so the final speed is equal to root 2 over m times w net. Well, there's only one force that was acting on the object, so w net is just w of the spring. So I can put, right, so v final is root 2 over 1.85 kilograms. Plugging in the mass, and W net is 2.178 joules. So when I plug that into my calculator, I get that this is 1.53 meters per second. Okay. So now let's talk about part C. And again, I'm going to encourage you, pause this video if you didn't get this part yet. Pause it and try and figure it out yourself, because this is just adding a constant force in alongside of the non-constant force. Okay, so I'm just going to assume that you did that, and now we'll go on to doing the problem. So now we're going to repeat the same calculation, but assume that the block is moving on a table and it has some kind of constant drag force. Okay, that's acting to slow it down. So there's a friction force now acting on it. So we still have this same relationship, right? Velocity final is equal to root 2 over m times w net. But now w net is going to be w from the force, from the spring force plus the work from the drag force. Okay, now the drag force, what's the work done by the drag force? Well, work is, well, this is nice because at least the drag force is kind of nice because it's constant. Okay, it's a constant drag force. So we can just use this simple relationship, right, where FD dot with the displacement. Okay, well, the displacement is entirely in the positive x direction, right? And it was, how much did the thing move? 0.11 meters. X hat would be the displacement. So the drag force, right, is pointing in the opposite direction. So the two vectors are anti-parallel. So the dot product between two anti-parallel vectors is negative the magnitude of each one of them. So this will be negative 7 newtons times 0.11 meters, or minus 0.77 joules. So that's how much work is done, right, by the drag force. The work done by the spring force will be exactly identical, exactly the same. So then my net force will be, it was 2.178 joules for the spring force plus negative 0.77 joules for the drag force. Okay, notice that the net amount of work is going down now because the drag force was doing negative work on it. The amount of work done by the spring is exactly the same. We just have another contribution here. And this is going to give us a net work of 1.41 joules. Okay, so that's the net work now. Plugging that in to our formula, we then have that the velocity will be 1.23 meters per second. So, right, note that this is less than the 1.53 meters per second, which we got without the drag force. So, unsurprisingly, the drag was introduced and the velocity went down. All right, so we can move on. Okay, now here is a little bit more complicated one where the force law depends on x squared. I'm running long on time, so we're almost at 50 minutes, so I don't have time to do this. But you can see example 7.6 in your textbook. I would encourage you to do that. All right, let's just wrap up this chapter, chapter 7 on work. So remember, work is a dot product between force and displacement when the force and the displacement, say, are constant. Work done by, say, a varying force, right, a force that varies over displacement, requires an integral. So this, which simplifies to that. And kinetic energy is the energy of motion. And the link between kinetic energy and work is the work energy principle. And the work energy principle, or as I like to call it, the WEP, right, WEP for short, says that the net work done on an object equals the change in the object's kinetic energy, or 1/2 mv final squared minus 1/2 mv initial squared. So that will sum up chapter 7, and I hope that you understood dot products and integrals enough from our previous lectures to be able to do now work on work from non-constant forces. If not, then go back and review those lectures, or do some extra problems. Look at the example problems in your book. Going to have to be able to do integrals, at least integrals over polynomials, and do dot products in order to do work. Now, next time we will move on to chapter 8, where we will finally cross our bridge all the way over from the force to the from the language of forces to the language of conservation of mechanical energy. And we will have a whole nother language that we can use then to understand physical systems and their dynamical properties. Okay, goodbye.